On a night like any other, in an observatory where computers hum and telescopes sweep the sky in automated patterns, a detection algorithm flags something unusual. The object moves against the background stars, but its trajectory does not match the elliptical paths of solar system natives. It approaches from above the ecliptic plane, that flat disk where planets orbit, coming in at an angle that suggests deep space origins. The designation follows standard protocol 3I Atlas, meaning the third confirmed interstellar object, discovered by the Asteroid Terrestrial Impact Last Alert System, only took humanity 4 billion years to develop the technology to notice. The comet appears first as a faint smudge in digital images, pixels barely distinguishing it from noise. Photons that began their journey in the cold between stars now strike silicon detectors, converting ancient light into electrical signals, into data points, into the first hints of a visitor's composition and speed. Astronomers calculate its velocity relative to the Sun too fast for a bound orbit, moving at speeds that can only mean it will pass through and never return. The hyperbolic trajectory curves through the inner solar system like a thrown stone arcing through a room, touching nothing, changing nothing, already committed to departure before arrival is complete. In those first observations, the comet shows a faint coma, that cloud of gas and dust that distinguishes comets from asteroids. Sunlight pressure pushes material away from the nucleus, creating a tail that always points away from the Sun regardless of the comet's direction of travel. This is not new information. Humans have understood comet tails since the 17th century, but each comet's particular chemistry remains unique, a fingerprint of its formation environment. Spectrographs begin their work, splitting the comet's reflected and emitted light into component wavelengths, searching for the dark lines and bright bands that reveal molecular composition. The discovery triggers a cascade of follow-up observations. Telescopes around the world turn toward the coordinates, gathering photons while the opportunity remains. Time-sensitive astronomy operates under the constraint of celestial motion. Objects do not wait for convenient scheduling or optimal weather. Cloudy skies mean lost data. Equipment failures mean permanent gaps in the observational record. Every night the comet travels millions of kilometers farther along its path, growing brighter as it approaches the Sun, or dimming as it recedes. And the window for detailed study narrows with each passing hour. Astronomers note the comet's absolute magnitude, its intrinsic brightness before accounting for distance and phase angle. The nucleus, that solid core of ice and rock, measures perhaps a few kilometers across small by planetary standards, enormous by human ones. If one could stand on its surface, the horizon would curve sharply, gravity so weak that a strong jump might achieve escape velocity, but no one will stand there. The comet passes through the inner solar system only once, and by the time it departs, it will be too far and too faint for anything but the largest telescopes to track. The data accumulates in archives, each observation tagged with timestamp and filter and exposure duration. Orbital elements refine with each new position. Measurement eccentricity greater than 1, confirming the hyperbolic path. Inclination steep relative to the ecliptic. Perihelion distance calculated to within meters. The comet will approach the Sun, but not dangerously close, no dramatic solar grazing. No spectacular disruption, only a gradual warming as frozen volatiles sublimate into vacuum. The transformation from ice to gas occurs at the molecular level, water molecules breaking free from the solid matrix, carbon dioxide sublimating even at temperatures where water remains frozen, each species responding to sunlight's energy according to its own particular physics. Somewhere in the comet's structure, stresses accumulate. Temperature gradients create differential expansion. Sunward surfaces warm, while shadowed regions remain cold. The nucleus rotates, tumbling chaotically rather than spinning smoothly, its irregular shape preventing stable rotation. Centrifugal forces pull outward, while the weak self-gravity pulls inward. And the frozen matrix that holds everything together begins to experience strain. Comets are not solid like rock. Their density suggests porosity. empty spaces between grains, ice mixed with dust in a delicate architecture that formed in the cold and calm of interstellar space or the outer regions of a protoplanetary disk. That structure, preserved for millions or billions of years in the cold dark, now faces the sun's radiant pressure for the first time in its journey. Observers notice something unexpected in subsequent images. The comet's brightness increases more rapidly than models predict for its approach distance. Photometric measurements show fluctuations inconsistent with simple rotation. Enhanced image processing reveals structure in the coma not the smooth, symmetric envelope expected from a single nucleus, but multiple condensations, distinct bright regions that suggest fragmentation has begun. The interstellar visitor is breaking apart, only took crossing light years of space to arrive, and the sun's warmth undoes it in weeks. The nucleus of 3I Atlas, before fragmentation, represents a time capsule from another stellar system. Its composition reflects the chemistry of the molecular cloud where it formed. Temperatures and pressures and elemental abundances determined by conditions near a different star. Perhaps billions of years ago, ice dominates the structure water ice most abundantly, but also frozen carbon monoxide, carbon dioxide, methane, ammonia, each compound condensing at specific temperatures during the comet's formation. Mixed throughout this frozen matrix are dust grains, silicates and carbonaceous particles, some possibly predating the comet itself, inherited from previous generations of stellar evolution and ejected into interstellar space by supernovae or stellar winds. The architecture of a comet nucleus follows no simple geometry. High-resolution images of other comets, captured during spacecraft flybys, reveal surfaces pitted and fractured, with steep cliffs and smooth plains and regions of active outgassing, where jets of sublimating ice burst through the crust. Some areas remain dark, covered in a layer of dust left behind as ice beneath sublimates away, creating an insulating blanket that slows further loss. Other regions expose fresh ice, bright and reflective, where recent fractures or impacts or thermal stress have broken through the darker surface layer. The internal structure likely consists of loosely bound aggregates, dust and ice weakly cemented together, with empty spaces between grains accounting for the low overall density. Scientists measure comet density through observations of their gravitational effects on passing spacecraft, or by analysing how quickly they respond to non-gravitational forces, the rocket effect of outgassing that gently pushes the nucleus in directions not predicted by gravity alone. The numbers consistently suggest densities far below that of solid ice, typically between 0.4 and 0.6 grams per cubic centimetre. Water ice itself has a density of about 0, and needs so cometary nuclei must contain substantial void space, perhaps 50% or more of their volume consisting of vacuum, of nothing. This porous structure forms during accretion in the outer regions of protoplanetary disks, where particles collide gently and stick through ice sintering and electrostatic forces rather than compacting into solid masses. For 3 Atlas specifically, the interstellar origin adds another layer of mystery. Did it form in orbit around its parent star, then get ejected through gravitational interactions with giant planets, a common process that populates the Oort cloud around our own sun? Or did it condense in interstellar space itself, within a dense molecular cloud, never experiencing the warmth of a nearby star until entering our solar system? The chemistry might reveal clues certain isotopic ratios, particular molecular species, abundances of noble gases trapped in ice, but these measurements require close approach or sample return, neither available for a fast-moving interstellar visitor. The organic compounds present in comets represent some of the solar system's most primitive materials. Spectra reveal signatures of complex carbon chemistry, long-chain hydrocarbons, aromatic structures, amino acid precursors. These molecules form through radiation processing of simple ices, where cosmic rays and ultraviolet photons drive reactions that would never occur at the cold temperatures where comets exist. Over millions of years, Methane ice slowly transforms into more complex compounds, building up a reservoir of organic chemistry that predates life itself. When comets delivered these materials to the early Earth, they provided not just water, but also the chemical building blocks necessary for biology. Only took the right molecules arriving at the right time in the right quantities, which happened over and over across millions of years of heavy bombardment. The comet's journey before discovery remains largely unknown. Tracing its orbit backward through gravitational simulations can identify possible origin regions, but the uncertainties grow with each million years of backward integration, gravitational perturbations from passing stars, the galaxy's overall gravitational field, even the pressure of interstellar gas and dust, all influence trajectories over such timescales. Perhaps 3I Atlas spent most of its existence drifting in interstellar space, its parent star long since moved away through galactic rotation. Perhaps it orbited a distant red dwarf in a wide, weakly bound path, eventually perturbed by a stellar encounter into an escape trajectory. The velocity vector, while precisely measured relative to our Sun, does not point back unambiguously to any particular star system currently visible. The frozen volatiles within the nucleus exist in different phases and layers. Water ice dominates the outer layers and makes up perhaps 70 to 80% of the total ice mass. Carbon monoxide ice, more volatile than water, concentrates in colder inner regions or sublimates away more readily, creating an enrichment in the coma relative to the nucleus. Carbon dioxide forms somewhere between these extremes, sometimes existing as pure ice, sometimes trapped within the water ice matrix as a clathrate hydrate. These different volatiles sublimate at different temperatures, carbon monoxide even at distances beyond Jupiter's orbit. Water ice only inside Mars's orbit. So a comet's activity evolves as it approaches the Sun, different chemical species dominating the coma at different distances. Dust particles released from the nucleus range from nanometers to centimeters in size. The smallest grains scatter sunlight efficiently, creating the visible coma and tail. Larger particles follow ballistic trajectories, less affected by radiation pressure, eventually spreading around the comet's orbital path as a debris stream. If Earth's orbit later intersects this stream, the particles burn up in the atmosphere as meteors, each bright streak representing a tiny fragment of interstellar material, atoms forged in another star's fusion reactions, now glowing at thousands of degrees as friction with air molecules converts kinetic energy to light and heat. Only took crossing between star systems to end as a momentary flash above someone's night sky. The surface temperature of the nucleus, even at perihelion, remains below 0 Celsius in most locations. Only the most directly illuminated regions approach the freezing point of water, and even then only briefly each rotation cycle. Shadowed areas never warm significantly, maintaining temperatures closer to those of deep space. This temperature distribution drives the asymmetric outgassing that creates jets and active regions rather than uniform sublimation across the entire surface. The warmest spots lose ice rapidly, creating pits that deepen over time, while cold regions accumulate dust and remain largely inactive, preserving ancient ice beneath a protective layer. The mystery of what holds such a fragile object together for so long, only to fail during solar approach, relates to the specific mechanical properties of ice at very low temperatures. Cold ice behaves more like rock than like the slippery frozen water familiar from Earth's surface. At temperatures below -100 Celsius, ice becomes hard and brittle, strong in compression but weak in tension. The thermal shock of rapid warming, the spin-up from asymmetric outgassing, the mechanical stress of differential expansion all combine to exceed the tensile strength of frozen matrix, and cracks begin to propagate through the structure. Light carries information across the vacuum between comet and observer. Photons reflected from the nucleus and scattered by dust grains in the coma arrive at Earth-based telescopes after a journey of minutes or hours, depending on the comet's distance. But the light itself contains more than brightness, its spectrum. The distribution of wavelengths from ultraviolet through visible to infrared encodes details of molecular composition, temperature, velocity, and physical processes occurring within the coma, spectroscopy, the analysis of light by wavelength, transforms photons into chemistry. When sunlight strikes molecules in the comet's coma, several processes occur. Some photons simply scatter, bouncing off dust grains or reflecting from gas molecules without changing wavelength, creating the continuous spectrum that makes the coma visible. Other photons have energies precisely matching the difference between molecular energy levels, and these get absorbed. The molecules then re-emit photons at characteristic wavelengths as they return to lower energy states, creating emission lines in the spectrum. Still other photons pass through the coma but with specific wavelengths removed where molecules absorbed them, creating absorption lines against the background solar spectrum. Each molecule has its own unique pattern of lines, a fingerprint determined by quantum mechanics and molecular structure. Water vapor shows prominent emission lines in ultraviolet and infrared wavelengths. The hydroxyl radical, formed when solar ultraviolet light breaks apart water molecules, produces particularly strong lines that astronomers use as a proxy for measuring water production rates. Observations of 3I Atlas reveal these hydroxyl signatures clearly, indicating active sublimation of water ice. The intensity of the lines, combined with models of how hydroxyl forms and disperses in the coma, allows calculation of how many water molecules per second escape from the nucleus, typically billions of kilograms per day, for an active comet near perihelion. Only took the sun's energy arriving over weeks to boil away mass that accumulated over millions of years. Carbon-bearing molecules appear throughout the spectrum. Cyanogen, CN, creates distinctive violet bands visible in the blue portion of the spectrum, contributing to the slightly greenish colour that some comets display. The carbon chain molecules C2 and C3 produce additional emission features. Carbon monoxide, abundant in many comets, requires ultraviolet observations to detect directly, but its dissociation product, atomic carbon, emits at wavelengths accessible to ground-based telescopes. The relative abundances of these carbon species vary between comets, reflecting different formation conditions or evolutionary histories, and measurements of 3I Atlas show ratios consistent with some solar system comets, but perhaps subtly different. Though uncertainties make definitive statements difficult, sodium emission lines appear unexpectedly strong in some observations of fragmenting comets. Sodium atom, released from dust grains by solar heating or photon bombardment, fluoresce efficiently in sunlight, producing two bright yellow-orange lines that can be detected even in small telescopes. The presence of sodium suggests silicate dust, minerals containing sodium bound in crystal structures, now breaking down as dust grains warm in the inner solar system. These grains themselves formed in the circumstellar disk around the comet's parent star. Minerals condensing from hot gas or inheriting from earlier stellar generations, now revealed through their characteristic glow. Isotopic ratios, measured through high-resolution spectroscopy, provide clues to formation conditions. The ratio of deuterium to hydrogen in water, for example, varies depending on temperature during ice formation. Colder environments tend to concentrate deuterium relative to hydrogen, through subtle differences in reaction rates and vapor pressures. Measurements of deuterium to hydrogen ratios in solar system comets show values several times higher than Earth's ocean water, suggesting formation at very cold temperatures in the outer reaches of the protoplanetary disk or beyond. For 3I Atlas, obtaining such precise measurements proves challenging the comet's rapid passage and faintness limit observing time, and the required spectral resolution demands long exposures. The data exists, archived and awaiting analysis, but definitive isotopic characterization may remain uncertain. The Doppler shift of spectral lines reveals velocity information. Molecules moving toward Earth emit lines shifted slightly toward shorter wavelengths, bluer, while molecules moving away emit lines shifted toward longer wavelengths, redder. By measuring these shifts, astronomers map the velocity field within the coma, determining how fast gas expands from the nucleus and whether expansion occurs symmetrically or jets dominate in particular directions. For 3I Atlas, Doppler measurements show gas velocities of several hundred meters per second, typical for water vapor sublimating from ice at around 200 Kelvin. The velocity distribution appears somewhat asymmetric, suggesting non-uniform outgassing, possibly related to the fragmentation process or to active regions on the rotating nucleus. Infrared spectroscopy accesses different molecular features than visible light observations. Water ice itself, not just water vapor, shows characteristic absorption bands in the near-infrared, allowing direct detection of exposed ice on the nucleus or in large grains. Carbon dioxide ice produces a strong absorption feature at 4.3 micrometers wavelength. Organic compounds, particularly those containing carbon-hydrogen bonds, create a complex forest of absorption lines throughout the infrared spectrum. These observations require space-based telescopes or high-altitude aircraft, since Earth's atmosphere absorbs most infrared light, but when available, they provide details about solid-phase materials rather than just the gas-phase molecules seen in visible spectra. The mystery of what spectroscopy cannot reveal remains significant. Many molecular species lack strong transitions at accessible wavelengths. Others exist in abundances too low for detection above noise. The nucleus itself, hidden beneath the coma's bright glow, reflects only a tiny fraction of the total light, making direct spectroscopy of its surface nearly impossible, except for the largest, closest comets. And the three-dimensional structure of the coma, the actual distribution of molecules and dust in space rather than projected onto the sky, must be inferred through models and assumptions rather than measured directly. Only took decades of astronomical observations to realize how much remains invisible even in clear detection. Polarimetry, the measurement of light's polarization state, adds another dimension to comet studies. Dust grains preferentially scatter light in ways that create partial polarization, and the degree and direction of polarization depend on grain size, composition, and shape. Observations of 3I Atlas in polarized light show patterns consistent with silicate and carbonaceous dust, with grain sizes ranging from submicrometer to tens of micrometers. The polarization degree increases with phase angle, the angle between sun, comet, and observer, following patterns seen in solar system comets. This similarity suggests that despite its interstellar origin, the comet's dust properties do not differ dramatically from local comets, perhaps indicating universal processes in dust formation around stars. The sun's radiation reaches the comet nucleus as electromagnetic waves across the spectrum, from radio to gamma rays, though most energy arrives as visible and infrared light. At the comet's distance, perhaps 2 astronomical units from the sun during the observational period, solar flux delivers roughly 1/4 the energy that reaches Earth's orbit, still sufficient to drive significant activity. Photons strike the nucleus surface and convert to heat through absorption, warming the ice and dust mixture according to its thermal properties and albedo, the fraction of light reflected rather than absorbed. Dark surfaces absorb more energy than bright ones. Fresh ice reflects perhaps 50 to 70% of visible light, appearing relatively bright. But comet nuclei often display albedos as low as 3 or 4%, darker than coal, darker than asphalt. This darkness comes from the accumulated dust lag deposit, the residue left behind as ice sublimates. Each layer of ice that vaporizes leaves its embedded dust particles on the surface, building up a dark crust that insulates underlying ice while absorbing solar energy efficiently. The crust's thermal conductivity determines how quickly heat penetrates to subsurface ice layers. If conductivity is low, as expected for loosely packed dust, then surface temperatures can rise considerably, while ice just centimeters below remains frozen and stable. When ice reaches its sublimation temperature at the local pressure, molecules begin transitioning directly from solid to gas without passing through liquid phase. Water ice sublimates noticeably at temperatures around 180 to 200 Kelvin at the pressures found on a comet nucleus, where atmospheric pressure essentially equals the vapor pressure of the ice itself, essentially zero by Earth standards. Carbon dioxide sublimates at even colder temperatures, around 150 Kelvin, while carbon monoxide becomes active at temperatures below 100 Kelvin. These different sublimation thresholds mean that a comet's activity changes character as it approaches the Sun first. Carbon monoxide drives activity in the outer solar system, then carbon dioxide takes over, and finally water dominates close to perihelion. The sublimation process requires energy, the latent heat of sublimation, which must be supplied by absorbed sunlight. For water ice, this amounts to approximately 2.8 million joules per kilogram, a significant energy requirement. The rate of sublimation depends on temperature through the Clausius-Clapeyron equation, a relationship derived from thermodynamics that describes how vapor pressure increases exponentially with temperature. Small temperature differences produce large changes in sublimation rate, so a nucleus does not lose ice uniformly, but rather develops active regions where local conditions favour rapid loss. As molecules leave the surface, they carry away both mass and energy. Each departing molecule removes not only its own mass, but also the thermal energy invested in breaking it free from the ice matrix. This cooling effect partially counteracts solar heating, establishing an equilibrium temperature lower than would exist without sublimation. The balance between incoming solar energy and outgoing energy from sublimation and re-radiated heat determines the steady-state surface temperature. For actively sublimating water ice in direct sunlight near 1 astronomical unit, this equilibrium temperature reaches approximately 200 Kelvin, cold by terrestrial standards but warm enough to drive vigorous activity. The sublimating gas does not escape instantaneously into vacuum. Near the surface, molecules collide frequently enough to constitute a thin atmosphere, a collisional regime where gas dynamics rather than ballistic trajectories govern flow. Gas pressure builds up beneath any surface crust, and if the crust lacks sufficient permeability, pressure can reach levels that fracture the crust explosively, producing jets and outbursts. These jets appear as bright streaks in images, concentrated streams of gas and entrained dust shooting away from specific locations on the nucleus. Only took the mechanical strength of frozen dust to contain the pressure, and once exceeded, the structure fails locally while surrounding regions remain intact. The temperature distribution across the nucleus surface varies dramatically with local time and latitude. Near the subsolar point, where sunlight strikes most directly, temperatures reach their maximum. At the terminator, the boundary between day and night, temperatures drop rapidly as solar input ceases. On the night side, the surface cools through thermal radiation, emitting infrared light into space and approaching equilibrium with the very cold nucleus interior. This day-night temperature cycle drives thermal stress surface materials expand when heated and contract when cooled, creating mechanical strain that accumulates over repeated rotation cycles. For an irregular nucleus tumbling chaotically, the pattern of heating and cooling becomes complex, with some surface regions experiencing more extreme cycles than others. Rotation affects sublimation patterns through changing which regions face the Sun. A nucleus spinning with a period of several hours brings each surface location through a complete temperature cycle during each rotation. Faster rotations spread solar heating more evenly, reducing peak temperatures but raising average temperatures on previously shadowed regions. Slower rotation allows deeper temperature extremes, with sunlit areas becoming very hot while night sides remain very cold. The observed brightness variations in 3E Atlas, fluctuating on timescales of hours, suggest rotation periods in that range, though the fragmenting nature of the nucleus complicates interpretation of the light curve. The mystery of heat transport within the nucleus remains poorly understood. Does thermal energy penetrate through solid-state conduction alone? Or does sublimating ice within the porous interior create convective-like flow, carrying heat deeper through the movement of gas molecules through pore spaces? Models suggest that for typical thermal conductivities expected in comet material, solar heat penetrates only centimeters to perhaps a meter during a single apparition through the inner solar system. Deeper interior remains pristine and cold, insulated by outer layers, only took most of the nucleus volume remaining untouched by the Sun's influence, preserved in its original state despite the dramatic activity visible at the surface. The thermal stress from differential expansion contributes to fragmentation. When one side of the nucleus heats while the other remains cold, the warm side expands while the cold side does not, creating bending moments and shear stress. If the nucleus contains pre-existing fractures or weak zones, planes where ice cohesion is lower, these stresses concentrate at such defects and propagate cracks through the structure. The process resembles how a glass dish can shatter when exposed to rapid temperature change. Thermal shock overwhelming material strength for a comet nucleus, already porous and weakly bound. The threshold for failure sits lower than for solid rock. The first sign of fragmentation appears as a subtle asymmetry in brightness measurements. Photometric monitoring shows the comet brightening faster than predicted for its decreasing solar distance, suggesting increased active surface area. Additional observations reveal structure in the coma, not one central condensation, but several, distinct bright regions separating slowly over days. Image processing techniques that remove the smooth coma envelope to enhance faint features show multiple nuclei, each surrounded by its own smaller coma, all embedded within the larger cloud of gas and dust from the original body. Fragmentation events in comets occur through several mechanisms. Rotational disruption happens when spin rate exceeds the threshold that self-gravity and material strength can contain, literally tearing the object apart through centrifugal force. Thermal stress fracturing occurs when temperature gradients create mechanical strain beyond what the ice matrix can withstand. Sublimation-driven erosion can undercut structural features, creating unstable overhangs that collapse. Impact by small meteoroids might trigger fragmentation in an already weakened nucleus. For 3I Atlas, the timing of fragmentation during solar approach suggests thermal processes dominate, though distinguishing between rotational spin-up and pure thermal stress remains difficult from observations alone. The fragments separate at velocities of meters per second, slow by human standards but sufficient to carry them apart over days and weeks. Each fragment follows a slightly different orbit, modified by the initial separation velocity and ongoing outgassing that acts as gentle rocket propulsion. Gravitational attraction between fragments remains negligible objects kilometers apart, with masses measured in billions of kilograms exert essentially no pull on each other. The swarm disperses not through active repulsion, but through each fragment pursuing its own independent path through the solar system's gravitational field, each responding slightly differently to solar radiation pressure and outgassing forces. Observations track the brightest fragments individually, assigning provisional designations to distinguish them in reports and databases. Fragment A, the brightest, appears to retain most of the original nucleus mass. Fragment B, somewhat fainter, separates at roughly 50 meters per second based on position measurements across several nights. Fragment C emerges later, possibly a secondary break from Fragment A. Fainter fragments likely exist but remain undetected, lost in the glare of the brighter pieces or simply too small and distant to produce sufficient scattered light for detection. Only took the parent nucleus breaking apart to create a multitude, most of which pass through the inner solar system entirely unnoticed. The size distribution of fragments follows patterns seen in other disrupted comets. Typically, one or two large pieces dominate, carrying most of the original mass, while numerous smaller fragments contain the remainder. This hierarchy reflects fracture mechanics' large-scale weaknesses. Major planes of defect break first to create the primary fragments, while secondary fractures within those pieces produce smaller components. The exact distribution depends on the nucleus's internal structure, the pattern of strength variation, and the specific stress history experienced during fragmentation. No two comets break identically, but statistical patterns emerge across multiple events. Each fragment continues sublimating, creating its own coma and tail. The smaller fragments, with higher surface area to volume ratios, lose mass more rapidly in proportion to their size. A fragment 1/10. The diameter of the original nucleus has 1/100th the volume but 1/10th the surface area, resulting in 10 times faster relative mass loss. Small fragments thus fade quickly, depleting their volatile inventory in weeks rather than months, sometimes disappearing entirely as ice sublimates away to leave only a loose collection of dust too diffuse to remain gravitationally bound. The larger fragments persist longer, visible for months as they continue their hyperbolic departure from the inner solar system. The separation velocity combined with orbital mechanics creates geometric patterns in the fragment distribution. Initially, the fragments cluster together, barely resolved in images. Over time, they spread along the parent comet's orbit, forming a linear train of objects, each following nearly the same path, but with slight offsets in timing. If viewed from above the solar system, the fragments would appear strung out like beads on a wire, marking the comet's trajectory. Cross-track separation, perpendicular to the orbit, occurs more slowly because the separation velocities have only small components in that direction. The swarm elongates preferentially in the along-track direction. Observers calculate which fragments might approach Earth's orbit, seeking potential meteor shower activity. When Earth passes through the debris stream left by a fragmenting comet, particles burn up as meteors, creating a shower radiating from the constellation where the intersection occurs. For 3I Atlas fragments, orbital calculations show small probability of intersection. The comet's hyperbolic path and high inclination place most debris outside the plane of Earth's orbit. Perhaps in the distant future, after gravitational perturbations by planets shift the debris stream's nodes, an intersection might occur, or perhaps not. The solar system is vast and orbital paths rarely coincide. Only took the specific geometry of approach to almost guarantee no future meteor displays from this particular visitor. The mystery of what triggered fragmentation at this particular time and location remains speculative. Why did the nucleus survive millions or billions of years drifting through interstellar space, and additional months approaching the Sun, only to fragment during a specific week of its passage, perhaps a pre-existing fracture propagated slowly under thermal stress, reaching critical length only at that moment? Perhaps rotation rate gradually increased from asymmetric outgassing until centrifugal stress exceeded cohesive strength. Perhaps multiple factors combined thermal stress weakening material strength, while rotation provided the final mechanical load. Comet nuclei do not carry flight recorders, do not preserve evidence of their structural history and accessible form, so definitive explanation requires inference from fragmentary evidence. The scientific value of observing fragmentation events lies partly in understanding material properties. Knowing the stress conditions under which a nucleus breaks reveals its tensile strength, compressive strength, cohesion between ice and dust. These properties determine how comets respond to other forces, tidal stress during close planetary approaches, impact by meteoroids, spin up from outgassing torques. Understanding comet strength matters for potential deflection strategies should a comet ever threaten Earth impact. Though the probability remains low, more fundamentally, material properties inform models of how comet nuclei form, whether through gentle accumulation of particles or more energetic processes involving compaction and sintering. Each fragment of 3I Atlas traces its own trajectory through space, governed by gravity and subtle non-gravitational forces. The gravitational component follows Newtonian mechanics, solved through equations that Isaac Newton formulated in the 17th century, and that remain accurate for objects moving at speeds far below the speed of light in regions where space-time curvature remains negligible. The Sun's gravity dominates, pulling each fragment along a conic section path determined by the fragment's velocity and position. For these fragments, as for the parent comet, the trajectory type is hyperbolic open curves that approach from infinity and depart toward infinity, never closing into elliptical orbits. The orbital elements that describe each fragment's path include 6 parameters: semi-major axis, eccentricity, inclination, longitude of ascending node, argument of perihelion, and mean anomaly at epoch. For hyperbolic orbits, the semi-major axis takes negative values by convention, and eccentricity exceeds unity. The eccentricity for 3I Atlas fragments measures perhaps 1.3 or 1 phi, meaning the orbit's opening angle is relatively narrow, not the extremely elongated hyperbolas that would result from eccentricities of 10 or 100. The inclination, approximately 40 degrees relative to the ecliptic plane, means the comet approaches from well above or below the planetary disk, crossing through at a steep angle during its perihelion passage. As fragments separate, their orbital elements diverge slightly from the parent body's values. A separation velocity of 1 meter per second, sustained over 1 day, changes position by roughly 86 kilometers. This displacement, small compared to astronomical distances, nevertheless alters the orbital elements measurably. The fragment's perihelion distances might differ by thousands of kilometers, their time of perihelion passage by hours or days. Over months, these small differences accumulate into large geometric separations, the swarm dispersing along and across the original orbital path. Non-gravitational forces modify the purely gravitational trajectory. Outgassing creates a rocket effect. Molecules ejected from the nucleus carry momentum, and by conservation of momentum, the nucleus recoils in the opposite direction. For a symmetric, non-rotating nucleus with uniform sublimation, these forces average to 0, but real nuclei rotate and sublimate asymmetrically, creating net forces that accumulate over time into measurable orbit changes. The effect is parameterized in orbital fitting as the non-gravitational parameters A1 and A2 representing radial and transverse accelerations. For active comets, these parameters can produce position changes of thousands of kilometers over months, comparable to the position uncertainty from measurement noise. The fragments' trajectories, projected forward in time, reveal their futures. Most will depart the inner solar system within months, receding beyond the orbit of Jupiter and then Saturn, cooling as solar flux diminishes, eventually becoming inactive as temperatures drop below sublimation thresholds, even for the most volatile ices. The fragments will continue outward through the outer solar system, crossing the orbits of Uranus and Neptune over years, barely perturbed by these distant planets' weak gravitational influence. Beyond Neptune, in the region where the Sun appears merely as the brightest star rather than a dominant disk, the fragments will coast at a nearly constant velocity, perhaps 30 or 40 kilometers per second relative to the Sun. Escape velocity from the Sun at Earth's distance is approximately 42 kilometers per second. The fragments' velocities exceed this threshold, confirming their hyperbolic trajectories, unlike Halley's Comet returning every 76 years, or Hale-Bopp returning in millennia. These fragments leave permanently. The Sun's gravity will never turn them back. Their paths curve through perihelion but continue bending outward, asymptotically approaching straight lines as solar gravity's influence fades. In 1 million years, the fragments will have travelled roughly 30 trillion kilometers, nearly 1 light-year, entering the realm where other stars' gravity becomes comparable to the Sun's. The direction of departure, encoded in the velocity vector at perihelion, determines which stars the fragments might eventually approach. Astronomers project the trajectories forward through the galaxy, accounting for stellar motions and the galaxy's overall gravitational potential. The calculations show the fragments heading generally toward a region of sky in the constellation Pisces, not aiming at any particular star but passing through a volume of space where dozens of stars reside within a few light-years. In roughly 1 million years, the fragments might pass within a few light-years of one of these stars, close enough that the star's gravity could slightly alter the fragment's trajectory. But such encounters remain statistically rare and dynamically weak, changing the fragment's velocity by perhaps tens of meters per second, negligible compared to its overall speed. The mystery of whether the fragments will survive long enough to reach interstellar space relates to their structural integrity and volatile inventory. Will small fragments completely sublimate before leaving the inner solar system, their mass entirely converted to gas and dust? Will larger fragments develop protective crusts that preserve internal ice despite ongoing solar heating? The answer determines whether the fragments eventually become dormant comet nuclei, inactive lumps of rock and depleted ice drifting through the galaxy, or whether they disappear entirely, dispersing into a thin stream of particles too small and diffuse to ever be detected again. Only took the fragility of loosely bound aggregates to make survival uncertain even after escaping the sun's influence. Planetary perturbations during passage through the solar system modify trajectories in ways that depend sensitively on exact positions during planetary encounters. A fragment passing within Jupiter's Hill sphere, the region where Jupiter's gravity dominates over the Sun's, experiences deflection proportional to encounter distance and relative velocity. None of the 3I Atlas fragments pass close enough to any planet for major deflection. But even distant encounters at hundreds of millions of kilometers produce small changes that accumulate into position differences of millions of kilometers decades later. The chaotic nature of gravitational dynamics means that tiny uncertainties in initial conditions, measurement errors of meters in position, millimeters per second in velocity amplify exponentially over time, making long-term trajectory prediction inherently limited. Software integrates the equations of motion numerically, stepping forward in small time increments, calculating gravitational forces from sun and planets, and non-gravitational forces from outgassing, updating positions and velocities at each step. The calculation requires balancing accuracy against computational cost. Smaller time steps give more accurate results, but require more processing time. Larger steps run faster, but accumulate numerical errors. For trajectories spanning millions of years, even efficient algorithms require substantial computing resources, and the results carry large uncertainties that grow with projection time. Comet fragmentation has been observed throughout the history of systematic astronomical observation. In 1846, Wilhelm von Biela noticed that the periodic comet bearing his name had split into two distinct components, each with its own coma and tail, separated by approximately 250,000 kilometers. The two fragments returned in 1852, now farther apart, and then disappeared entirely, never observed as intact bodies again. Meteor showers in 1872 and 1885, occurring when Earth crossed the comet's former orbital path, revealed the fragment's fate: complete disintegration into a dispersed stream of particles, each grain burning briefly as it entered Earth's atmosphere. Only took a single fragmentation event to transform a periodic comet into a transient meteor shower. In July 1994, comet Shoemaker-Levy 9 collided with Jupiter in a series of impacts that marked the first time humans witnessed such an event in real time. The comet had fragmented during a close approach to Jupiter in 1992, tidal forces from the planet's gravity exceeding the nucleus's structural strength. 21 identified fragments, strung out along the orbital path like a cosmic pearl necklace, struck Jupiter's atmosphere over the course of a week. Each impact released energy equivalent to millions of megatons of TNT, creating dark scars in Jupiter's clouds visible from Earth-based telescopes. The fragments range from perhaps 1 to 2 kilometers in diameter, having broken from a parent nucleus estimated at 5 kilometers across before tidal disruption. Comet Linear, designated C1999S4, brightened rapidly in 2000 as it approached the Sun, then fragmented spectacularly into dozens of pieces. Observations captured the nucleus breaking apart in real time over hours and days, small condensations appearing, brightening, then fading as they dispersed into diffuse clouds. By the time the comet reached perihelion, no substantial nucleus remained, only an elongated cloud of dust and gas marking where the solid body had been. The fragmentation appeared to result from structural failure under thermal stress and rotation, the nucleus spinning faster as asymmetric outgassing created torques, until centrifugal force exceeded the material strength binding ice and dust together. Comet Schwarzmann-Wachmann 3 has fragmented progressively over multiple apparitions. First observed splitting in 1995, it has continued breaking into additional pieces during subsequent returns, each fragment then sometimes fragmenting further. By the 2006 apparition, dozens of identified fragments spread along the orbital path, ranging in brightness by factors of hundreds, suggesting size variations from hundreds of meters to just a few meters in diameter. The comet's repeated fragmentation suggests fundamental structural weakness, perhaps resulting from thermal processing during previous perihelion passages that created internal fractures and reduced cohesion. The statistical frequency of observed comet fragmentation suggests it is common but not universal. Perhaps 10 to 20% of comets show clear evidence of splitting during their observed apparitions, though this fraction represents a lower limit since subtle fragmentation might escape detection. The actual fragmentation rate could be considerably higher, with many events occurring when comets are too distant or too faint for detailed monitoring. Fragments smaller than a few tens of meters might never be detected individually, lost in the parent comet's coma or fading below detection thresholds within days of separation. Different fragmentation modes produce different observable signatures. Catastrophic disruption, where the nucleus breaks apart completely in minutes or hours, creates a sudden brightness increase as fresh ice surfaces begin sublimating, followed by rapid fading as small fragments deplete their volatile inventory. Gentle splitting, where one or two large pieces separate slowly over days, produces double nuclei that remain visible for weeks or months. Cascading fragmentation, where secondary breaks produce tertiary pieces that themselves fragment, creates complex hierarchical structures in images, clusters within clusters, each generation of fragments smaller and shorter lived than the previous. The observational bias toward detecting fragmentation during perihelion passage reflects both increased monitoring and increased physical stress. Comets brighten near perihelion, attracting more observational attention from both professional astronomers and amateur observers. Simultaneously, thermal stress peaks. Rotation rates may reach maximum from accumulated outgassing torques, and tidal forces from the Sun grow strongest. These combined factors make perihelion the most likely time for fragmentation to occur and be detected. Comets fragmenting at large solar distances, where stresses are lower but observations are sparse, might break apart entirely unnoticed. The historical record likely misses many fragmentation events before systematic photographic and digital sky surveys. Comets that split in antiquity, observed only through visual observations recorded in variable detail, might have fragmented without the event being recognized or recorded. The Great Comet of 1680, intensely observed by astronomers including Newton himself, showed no reported signs of fragmentation, but would subtle splitting have been noticed with the telescope technology of that era? The question remains unanswerable. Historical observations preserving only what observers chose to record and had means to detect. Modern automated surveys that monitor the sky continuously increase fragmentation detection rates. Telescopes that image the entire visible sky every few nights provide temporal coverage that can catch comets, brightening unexpectedly, or developing a symmetric morphology suggestive of splitting. When survey software flags unusual brightness changes or apparent motion inconsistent with predicted orbits, follow-up observations investigate further, often revealing fragmentation in progress. Only took continuous monitoring to reveal that comet disruption happens more frequently than telescopes pointed at individual targets would suggest. Each fragmenting comet a brief event in the sky's continuous transformation. The lesson from historical fragmentation events informs interpretation of 3i Atlas. The processes are familiar, documented in other comets, suggesting universal physics rather than exceptional circumstances. Comet nuclei are fragile, held together by material strength barely adequate for their structure, vulnerable to thermal stress and rotation and tidal forces. That an interstellar comet fragments similarly to solar system comets suggests similar internal structure, similar composition, similar formation processes operating around other stars as around our Sun. The universality of comet fragility spans the galaxy. The gravitational self-binding energy of a comet nucleus represents the work required to disperse its mass to infinity, separating every particle from every other against their mutual gravitational attraction. For a spherical body of uniform density, this energy scales with mass squared divided by radius, meaning larger objects are more strongly self-bound, but comet nuclei, with typical radii of 1 to 10 kilometers and masses of billions to trillions of kilograms, possess remarkably weak self-gravity. The escape velocity from a 5-kilometer radius nucleus might be only 1 or 2 meters per second, easily achievable with a gentle jump, laughably small compared to Earth's escape velocity of 11 kilometers per second. Such weak gravity cannot hold a fragmented object together through gravitational attraction alone. If thermal stress or rotation splits a comet nucleus into separate pieces, gravity provides essentially no force pulling them back together. The fragments drift apart at whatever velocity the splitting imparted, unrestricted by gravitational binding. This means that comet nuclei must possess material strength, cohesive forces between ice grains and dust particles, to maintain integrity against disruption. The relevant material property is tensile strength, the stress required to pull the material apart, rather than compressive strength, which resists squeezing together. Ice at very low temperatures behaves as a brittle solid with mechanical properties similar to rock. Laboratory measurements of pure water ice at temperatures below -100 Celsius show tensile strength of several megapascals, comparable to weak concrete. However, comet nuclei are not pure ice, but rather intimate mixtures of ice and dust, with substantial porosity, empty spaces comprising perhaps half the volume. This porous structure, along with microfractures and grain boundaries, drastically reduces bulk tensile strength compared to pure ice. Estimates based on observed fragmentation events and tidal disruption limits suggest effective tensile strength of comet nuclei ranges from a few hundred pascals to perhaps 100 kilopascals, spanning 3 orders of magnitude uncertainty. The uncertainty in material strength reflects the difficulty of measuring it remotely. Spacecraft encounters with comets provide surface images showing texture and morphology, but direct mechanical testing would require landing, drilling, or sample return, none of which occurred for most visited comets. Indirect inference from fragmentation behavior requires knowing the stress conditions during breakup, which depend on poorly constrained parameters like rotation rate, thermal conductivity, and internal structure. Different assumptions about these parameters lead to different calculated stresses, and therefore different inferred material strengths. The structure of comet nuclei, revealed by spacecraft imagery, suggests heterogeneous strength. Some regions display smooth plains, possibly dust mantles covering underlying ice, while other areas show rugged terrain, steep cliffs, and deep pits where structural collapse has occurred. The interface between different terrains might represent strength boundaries, zones where material composition or porosity changes, creating planes of weakness. When stress concentrates at such interfaces, fractures preferentially propagate there rather than through stronger surrounding material. The nucleus breaks along its weakest planes first. Rotation creates centrifugal stress that tries to pull a nucleus apart. For a uniformly rotating body, stress increases with the square of rotation rate, and with distance from the rotation axis. A nucleus spinning once every few hours experiences centrifugal acceleration of perhaps millimeters per second squared at its equator, trivial by terrestrial standards but approaching the level that weak cohesion can resist. If rotation rate increases, through torques from asymmetric outgassing gradually spinning up the nucleus over multiple orbits, eventually centrifugal stress exceeds tensile strength, and the nucleus breaks. The critical rotation period, the fastest spin before disruption, depends on material strength and density and shape. For typical comet parameters, critical periods fall in the range of hours to tens of hours. The mystery of how porous aggregates of ice and dust achieve even the modest strength they display relates to sintering processes. Sintering occurs when ice grains in contact gradually fuse together, forming stronger bonds through vapor transport and molecular diffusion. At very low temperatures, sintering proceeds slowly, but over millions of years, even slow processes produce significant strengthening. Additionally, small amounts of liquid water, possibly created by localized heating from radioactive decay or impact, could freeze into cements between grains, enhancing cohesion. The degree of sintering and cementing determines whether a nucleus behaves as a cohesive solid or a gravitational rubble pile barely held together. Observations of comet rotation rates provide indirect constraints on strength. Surveys of many comets show most rotate with periods between 6 and 30 hours, with very few rotating faster than 4 hours. This deficit of rapid rotators suggests that faster spinning nuclei either form rarely or fragment quickly, removing themselves from the observable population. The distribution cutoff at roughly 4 hours implies a characteristic strength threshold, with nuclei weaker than that threshold fragmenting if spun up to such rates. Only took measuring rotation periods across many comets to identify the statistical signature of mechanical limits. The distribution of spin rates also shows another pattern. Fragments from disrupted comets often rotate faster than typical intact comets, sometimes with periods of just 1 or 2 hours. This observation suggests that fragmentation itself involves rotational energy, perhaps through conservation of angular momentum as a larger, slowly rotating parent breaks into smaller, rapidly rotating fragments, or through torques during the separation event. Rapidly rotating fragments then face higher centrifugal stress, potentially leading to secondary fragmentation, creating a cascade where large, slow pieces break into medium-speed pieces that break further into small, fast pieces until material strength finally exceeds applied stress. The specific mechanism that holds 3I Atlas together before fragmentation and the specific failure mode that led to breakup remain uncertain. Did pre-existing fractures propagate under thermal stress until critical crack lengths were reached? Did rotation gradually accelerate until centrifugal force exceeded cohesive strength? Did sublimation erode supporting structures until gravitational stability failed? Multiple processes likely contributed. Their relative importance unknowable without direct structural measurements that spacecraft flybys to interstellar comets remain beyond current capability. Only took the sum of all stresses finally exceeding the sum of all strengths at some particular location within the nucleus, and fracture propagated from there through the rest of the structure. As fragments separate and sublimate, they leave behind trails of dust particles dispersed along their orbital paths. Each grain of dust, released from the nucleus when surrounding ice sublimated away, initially travels with the comet's velocity, but then responds to forces that affect small particles differently than large bodies. Radiation pressure from sunlight pushes on dust grains with force proportional to their cross-sectional area, while inertia resists acceleration in proportion to mass, which scales with volume. Small grains, with high surface area to mass ratios, accelerate more under radiation pressure than large grains, causing size-dependent trajectories that spread the dust into a dispersed cloud. The smallest grains, submicrometer particles, experience radiation pressure exceeding solar gravity. These particles accelerate outward from the sun, blown away by light like leaves in wind, achieving velocities of hundreds of meters per second over days and weeks. They form the Type II comet tail, the dust tail that curves gently away from the sun, its curvature reflecting the balance between the grain's initial velocity, inherited from the comet, and the radiation pressure acceleration perpendicular to the orbit. Medium-sized grains, from micrometers to millimeters, experience radiation pressure comparable to solar gravity, following trajectories intermediate between the comet's orbit and straight outward. Large grains, centimeters or larger, barely respond to radiation pressure and continue on nearly the same orbit as the nucleus that released them. The dust trail forms a tube-like distribution along the comet's orbital path, grains spread by their different responses to radiation pressure and by the velocity dispersion imparted during ejection. Gas drag in the inner coma accelerates some particles to velocities different from the nucleus rotation, creating ejection velocity distributions with typical speeds of tens to hundreds of meters per second. Over weeks and months, particles ejected at slightly different times and velocities spread along the orbit, while radiation pressure separates them perpendicular to the orbit according to size. The result is a structured debris stream, with smallest particles forming an outer envelope and largest particles concentrated near the original orbital path. If Earth's orbit intersects this debris stream, the particles enter the atmosphere at high velocity, typically tens of kilometers per second, and friction with air molecules heats them to incandescence. The glowing particle is a meteor, commonly called a shooting star despite being neither shooting nor a star. Most particles burn up completely at altitudes between 80 and 120 kilometers, their kinetic energy converted to heat and light in fractions of a second. Larger particles, centimeters or more in size, may survive the atmospheric passage and reach the surface as meteorites, though dust from comets typically remains too small and fragile for survival. The meteor shower activity from a debris stream depends on the stream's age and spatial density. Fresh streams, created by comets that fragmented or passed perihelion recently, contain high particle densities and produce strong showers if Earth intersects them. Old streams, spread by planetary perturbations and radiation effects over centuries or millennia, become diffuse, producing weak showers or none at all. The Perseid meteor shower, active every August, originates from Comet Swift-Tuttle and remains strong because the comet's relatively short orbital period of 133 years repeatedly replenishes the stream. The Andromedid shower, from the fragmented Biela's comet, produced spectacular storms in the 19th century, but faded to barely detectable rates by the 20th century as the debris dispersed. For 3I Atlas fragments, the hyperbolic orbit means no periodic replenishment. Whatever dust the fragments release during their single passage through the inner solar system represents the total amount that will ever exist from this source. The debris stream will gradually spread through perturbations and radiation effects, but no new material will be added. Eventual intersection with Earth's orbit depends on whether planetary gravitational perturbations shift the stream's orbital nodes, the points where the stream crosses the ecliptic plane, to coincide with Earth's position. The probability is low but non-zero, calculable through long-term dynamical integration but with large uncertainties. The composition of dust particles from 3I Atlas would reveal details about its interstellar origin if samples could be collected. Meteor spectrum observations during atmospheric entry show atomic emission lines from elements vaporized by heat: sodium, magnesium, iron, calcium. More detailed composition requires particle collection, either in the stratosphere using high-altitude aircraft or in space using collector plates exposed during orbital missions. Such collection has successfully captured interstellar dust grains passing through the solar system, identified by their high entry velocities and trajectories inconsistent with solar system origin. Whether any grains from 3I Atlas will ever be collected depends on dust production rates, particle trajectories, and whether any collection missions happen to be operating when the sparse debris cloud passes Earth's location. The dust's gradual dispersal transforms concentrated comet material into diffuse interplanetary medium. Over thousands of years, the dust trail spreads throughout the inner solar system, individual particles perturbed by planetary encounters, pushed by radiation pressure, affected by Poynting-Robertson drag. The subtle effect where absorbed and re-emitted photons gradually reduce a particle's orbital energy. Eventually the dust spirals into the sun, or is ejected from the solar system or collides with a planet or moon, each grain's trajectory ending in accretion or destruction. Only took the dust surviving interstellar space to be dispersed within a few millennia of entering a new stellar system. The timescale for dispersal brief compared to the aeons the material spent drifting between stars. The optical glow from dust in a comet's coma and tail dominates the comet's visual appearance. Gas makes up most of the mass released from the nucleus, but dust scatters sunlight more efficiently, producing the bright diffuse appearance visible to the eye or camera. The gas coma, while more massive, appears fainter and requires spectroscopy or specialized filters to observe clearly. This means that what we see when we look at a comet is primarily dust, not ice. The solid residue rather than the volatile component, visual appearance emphasizing the least abundant ejected material, while the dominant component remains largely invisible. Only took the quirks of light scattering to make comets appear as dusty clouds when fundamentally they are evaporating ice. The mystery of dust's detailed structure, the exact arrangement of minerals and organics within individual grains, requires microscopic examination, possible only for collected samples. Spacecraft missions to comets have captured dust particles for return to Earth. An analysis reveals grains with complex internal structure, mixtures of crystalline and amorphous phases, organic coatings on mineral cores, fluffy aggregates of smaller components. Each grain preserves a record of formation conditions and processing history, readable through careful analysis of composition and texture. For interstellar grains from 3I Atlas, such analysis would provide constraints on chemistry around other stars, on dust formation in different environments, but depends on the unlikely event of collection. The trajectory of 3I Atlas, traced backward through time, provides clues to its origin point in the galaxy. Astronomers reverse the comet's motion through computer simulations, undoing its path through the solar system and into the interstellar medium, accounting for the sun's motion through the galaxy and the gravitational influence of nearby stars. The calculations incorporate the local standard of rest, the average velocity of stars in the sun's neighborhood as they orbit the galactic center, and subtract this motion to reveal the comet's velocity relative to the surrounding stellar population. The residual velocity, the comet's peculiar motion, indicates whether it originated from a nearby star system or simply drifted through interstellar space for an extended period. The velocity vector points back toward a region of sky, but identifying a specific parent star requires matching both direction and timing. A comet ejected from a star system millions of years ago must have its parent star's motion traced backward through that same interval, accounting for each star's orbit around the galaxy. Stars near the Sun move at velocities of tens of kilometers per second relative to each other. So over 1 million years, a star travels roughly 30 parsecs, about 100 light-years. The volume of space within 100 light-years of any point contains hundreds or thousands of stars, and tracing each backward through time with sufficient precision to match the comet's trajectory proves computationally intensive and uncertain. Measurements of stellar positions and velocities come from missions like Gaia, which maps stellar parallax and proper motion with unprecedented precision. Parallax. The apparent shift in a star's position as Earth orbits the Sun directly measures distance. Proper motion, the star's movement across the sky over years, combined with radial velocity from Doppler shift, provides the full three-dimensional velocity vector. But even Gaia's precision has limits: distance uncertainties of a few percent, velocity uncertainties of kilometers per second. These uncertainties propagate through backward integration, growing exponentially in chaotic systems, limiting how far back in time and how precisely trajectories can be traced. The search for 3I Atlas's parent star examines stellar positions and velocities for close approaches in the past. If the comet's backward trajectory and a star's backward motion bring them within a few light-years of each other at the same time, that star becomes a candidate origin. But the analysis for 3I Atlas yields no clear match. Several stars show possible close approaches, but with uncertainties large enough that definitive association remains impossible. Perhaps the parent star is too faint or too distant to appear in current catalogues. Perhaps the ejection occurred so long ago that galactic dynamics have erased the trajectory connection. Perhaps the comet formed in interstellar space itself, accreting in a dense molecular cloud unattached to any stellar system. Red dwarf stars, the most common stellar type in the galaxy, produce planetary systems frequently, and those planets can eject comets through gravitational interactions. A red dwarf's low mass means its habitable zone, where liquid water could exist on planetary surfaces, lies close to the star, while its Oort cloud equivalent extends outward to distances comparable to solar system scales. Comets in such systems experience stellar flybys more frequently than solar system comets. Since the galaxy's stellar density in the Sun's neighbourhood includes many red dwarfs, any of thousands of nearby red dwarfs could have ejected 3I Atlas billions of years ago, the comet then wandering interstellar space until chance brought it near the Sun. The chemistry of 3I Atlas, particularly isotopic ratios, might constrain formation environment. Different stellar masses produce different abundances of elements through nucleosynthesis, and the material from which a planetary system forms reflects the average composition of molecular clouds enriched by previous stellar generations. A comet forming around a metal-poor star would show different elemental ratios than one forming around a metal-rich star. The ratio of oxygen isotopes, carbon isotopes, nitrogen isotopes all carry information about nucleosynthetic pathways and galactic chemical evolution. Unfortunately, measuring these ratios in a distant, fragmenting comet proves extremely difficult, and the observations of 3I Atlas do not provide sufficient spectral resolution for definitive isotopic determination. The timescale of interstellar travel depends on velocity and distance. A comet moving at 30 km per second relative to nearby stars travels 1 parsec, about 3 light-years, in roughly 100,000 years. To travel from a star 100 light-years away requires several tens of millions of years. Over such timescales, the comet experiences interstellar radiation, cosmic rays that slowly alter surface chemistry through radiolysis, the breaking of chemical bonds by high-energy particles. Organic molecules synthesized in the comet's birth environment undergo transformation, some molecules destroyed, others created, the chemistry gradually shifting toward an equilibrium determined by radiation flux and temperature. Only took millions of years of cosmic ray exposure to process the comet's surface layers, erasing some signatures of original formation while creating new compounds that would never form in a stellar system's warmer environment. Galactic dynamics introduce randomness into comet trajectories over long timescales, encounters with molecular clouds, regions of higher gas density in the interstellar medium, exert gravitational drag that slightly alters velocity. The galaxy's gravitational potential, not perfectly smooth but containing spiral arms and density waves, perturbs orbits, distant encounters with stars, passing within a few light-years, gravitationally deflect trajectories by small amounts. Each perturbation is minor, but accumulated over millions or billions of years, they randomize the comet's velocity vector, erasing information about initial direction. The comet's current trajectory reflects its recent history, the last few million years perhaps, but earlier origins become increasingly uncertain. The mystery of how many interstellar comets pass through the solar system undetected relates to observational biases and survey completeness. Telescopes detect comets by their brightness, which depends on size, activity level, and distance. Inactive comets, having lost their volatiles or developing thick inactive crusts, produce no coma and appear as faint asteroids, difficult to distinguish from solar system asteroids without careful trajectory analysis. Small comets, even if active, might not brighten sufficiently for detection. Comets passing through the outer solar system, beyond Jupiter's orbit, remain faint and fast-moving, easily missed. Estimates based on discovery rates of the few detected interstellar objects suggest that perhaps one passes inside Earth's orbit per year, with dozens per year passing through the outer solar system. Only took improving survey sensitivity to realize the solar system continuously receives visitors from interstellar space, most passing through entirely unnoticed. The chemical composition of ice within a comet nucleus reflects the conditions in the molecular cloud or protoplanetary disk where it formed. Different environments produce different relative abundances of frozen compounds, and measuring these abundances provides constraints on formation temperature, radiation field, and chemical processes. Water ice dominates most comets, comprising 70 to 80% of total ice mass. But the minor species carbon monoxide, carbon dioxide, methane, ammonia, formaldehyde, methanol carry disproportionate information about formation history. The ratio of carbon monoxide to water, for example, varies considerably between comets, with some showing CO/H2O ratios of a few percent, and others showing values 10 times higher, suggesting formation at different heliocentric distances or in different chemical regimes. Isotopic ratios provide even more precise formation diagnostics. The ratio of deuterium to hydrogen varies with temperature during ice formation, with colder environments preferentially incorporating deuterium relative to hydrogen through kinetic fractionation effects. Water molecules containing deuterium instead of hydrogen have slightly different vapor pressures and reaction rates, and at very low temperatures, these small differences accumulate into measurable enrichments. Comets measured to date show deuterium to hydrogen ratios in water ranging from about 1 to 3 times Earth's ocean value, indicating formation temperatures between 20 and 50 Kelvin, depending on specific models and assumptions. If 3I Atlas formed around a different star, its isotopic ratios might differ from solar system comets, revealing whether planetary system chemistry varies significantly between stellar environments. The oxygen isotope composition tells another story. 3 stable isotopes of oxygen exist: oxygen-16, oxygen-17, and oxygen-18, and their relative abundances depend on nucleosynthetic processes in previous stellar generations and on chemical fractionation during solar system formation. Most solar system materials plot along a specific line in oxygen isotope space, reflecting mixing between different primordial components. Cometry water, when measured with sufficient precision, shows oxygen isotope ratios consistent with this solar system signature, but uncertainties remain large enough that subtle differences might exist undetected. An interstellar comet from a different stellar environment might show a distinct oxygen isotope signature, shifted from the solar system line, providing definitive proof of extrasolar origin beyond the hyperbolic trajectory evidence. Carbon isotope ratios, specifically carbon-13 to carbon-12, vary in solar system bodies according to formation location and chemical processing history. The Sun's outer layers show a carbon isotope ratio of about 99 carbon-12 atoms for every carbon-13 atom. Cometry carbon in various molecular forms shows ratios close to this value, but with variations depending on molecule type and measurement technique. Carbon monoxide tends to show slightly different ratios than carbon dioxide, reflecting different formation pathways or fractionation during sublimation and chemical reactions. For 3I Atlas, the carbon isotope measurements remain insufficiently precise to determine whether values differ from solar system comets. The data existing but buried within measurement noise. Nitrogen in comets appears primarily as molecular nitrogen, ammonia, and cyanide compounds. The nitrogen isotope ratio, nitrogen-15 to nitrogen-14, shows significant variation across solar system objects, with some primitive materials enriched in nitrogen-15 by factors of 2 or 3 relative to the Sun's atmosphere. This enrichment likely reflects chemical processing in the cold outer solar system, or inheritance from the pre-solar molecular cloud. Cometary nitrogen shows intermediate enrichment, suggesting mixing of different components or processing under intermediate conditions. Whether interstellar comets show similar patterns or distinct signatures remains unknown, awaiting measurements precise enough for definitive comparison. Noble gas abundances and isotope ratios provide additional constraints. Noble gases: helium, neon, argon, krypton. Xenon do not form chemical bonds and must be physically trapped in ice as clathrate hydrates or adsorbed on grain surfaces. Their abundances depend on temperature, pressure, and ice composition during trapping. The isotope ratios of noble gases, particularly xenon, vary across solar system materials and show signatures of different nucleosynthetic processes. Cometary noble gases remain poorly measured due to their low abundances and the difficulty of detecting them spectroscopically. But in situ measurements from spacecraft missions that pass through cometary Comet have begun constraining these values. For interstellar comets like 3I Atlas, such measurements remain impossible without a dedicated mission. The organic compounds in comets, complex carbon-bearing molecules, form through multiple pathways. Some organics likely predate the solar system, forming in the interstellar medium through gas phase chemistry or on grain surfaces. Others formed within the protoplanetary disk through radiation processing of simpler ices. Still others may have formed within the comet nucleus itself over billions of years, as cosmic rays drove slow chemistry within the ice matrix. Distinguishing between these sources requires detailed molecular characterization, identifying specific compounds and their isotopic composition. Observations possible only through spacecraft encounters or sample return missions. The organic inventory of 3I Atlas remains largely unknown beyond detection of simple species like CN and C2, the complex chemistry invisible to remote spectroscopy. Amino acids, the building blocks of proteins, have been detected in samples returned from Comet Wild 2 by the Stardust mission. The presence of amino acids, along with other prebiotic molecules, supports scenarios where cometary delivery contributed to Earth's prebiotic chemistry. If amino acids formed commonly in comets throughout the galaxy, then every planetary system that experienced cometary bombardment received these chemical building blocks, perhaps making the emergence of life more probable than if each planet had to synthesize prebiotic molecules from scratch. The universality of cometary chemistry across different stellar systems remains an open question, testable only through analysis of interstellar comets or eventual missions to exoplanetary systems. The mystery of how much cometary chemistry varies between stellar systems relates to the universality of physical laws versus the diversity of stellar environments: carbon, oxygen, nitrogen, and hydrogen. The elements dominating cometary composition form in all stars and get distributed through space by supernovae and stellar winds. The chemistry they undergo in molecular clouds and protoplanetary disks follows quantum mechanics and thermodynamics, universal laws that operate identically everywhere. But the specific conditions, temperature, pressure, radiation intensity, elemental abundances vary between environments, potentially producing different chemical outcomes. Only took observing one interstellar comet closely enough to begin answering whether comets everywhere resemble those in our solar system. But the observations of 3I Atlas provide insufficient detail for definitive conclusions, leaving the question suspended between likelihood and uncertainty. Most of what exists in the 3I Atlas debris swarm remains invisible to our telescopes. The observational record captures the brightest fragments, those large enough and active enough to produce detectable coma and reflected light. But fragmentation events typically produce size distributions weighted heavily towards smaller objects for every fragment 1 kilometer across. Dozens or hundreds may measure only hundreds of meters, and for every 100-meter fragment, thousands of 10-meter pieces may exist. These smaller fragments, too faint to detect individually at the comet's distance, continue their hyperbolic trajectories unseen, silent travelers through the inner solar system. The size distribution of fragments follows power law relationships observed in other disrupted bodies. Asteroid family studies, examining the size distribution of fragments from ancient collisions, show consistent patterns where the number of objects increases rapidly with decreasing size. The exponent of this power law, typically between 2.5 and 3.5, means that reducing diameter by a factor of 10 increases fragment count by roughly 100 to 3,000 times. Applying similar scaling to 3I Atlas suggests that for the 3 or 4 tracked fragments of kilometer scale, hundreds of 100-meter fragments likely exist, along with tens of thousands of 10-meter pieces and millions of meter-scale fragments. Only took the mathematics of fracture mechanics to populate the swarm far beyond what telescopes reveal. Detection limits depend on distance, albedo, and activity level, a fragment 100 meters across. With typical comet albedo of 4% and located 2 astronomical units from both Sun and Earth, reflects barely enough sunlight to reach apparent magnitude 25 near the limit of large professional telescopes with extended exposure times. If the fragment develops a coma from sublimation, it brightens substantially, perhaps reaching magnitude 20 or brighter, depending on activity level. But if the fragment remains inactive, covered by an insulating dust mantle that prevents sublimation, it stays dark and essentially invisible. The majority of small fragments likely fall into this category, too small to maintain vigorous activity, their surface quickly mantled by dust, fading below detection within days of separation. Inactive fragments resemble asteroids more than active comets, and distinguishing them from the vast population of main belt asteroids requires careful trajectory analysis. An object on a hyperbolic orbit stands out immediately once multiple position measurements establish its motion. But obtaining those measurements first requires detecting the object. Survey telescopes that sweep the sky searching for near-Earth asteroids might occasionally image small 3I Atlas fragments, recording their positions without recognizing their interstellar origin. The objects appear in images as faint dots, indistinguishable from thousands of other faint dots, assigned provisional designations, then lost when follow-up observations fail to recover them. Some fraction of lost asteroids in databases may actually be interstellar fragments that passed through the inner solar system once and departed forever. The spatial distribution of fragments evolves with time. Initially clustered near the parent comet's position, they disperse through differential orbital velocities and non-gravitational forces. After months, the swarm spreads over millions of kilometers along the orbital path, individual fragments invisible to each other, each traveling through empty space with a nearest sibling too distant and too faint for mutual detection. The swarm forms not a cloud, but a sparse collection of isolated objects, connected only by common origin and similar trajectories, orphaned children of a disrupted parent wandering separately through the solar system. Radio observations offer alternative detection methods for inactive fragments. Radar systems transmit radio waves and detect echoes from solid objects, capable of detecting asteroid-sized bodies without relying on reflected sunlight. But radar detection range is limited. Even the most powerful planetary radar systems detect objects only within a few tens of millions of kilometers, and the signal strength decreases rapidly with distance. For fragments on hyperbolic trajectories, the window when they pass close enough for radar detection is brief, and unless observations are specifically scheduled, most fragments pass through undetected. Only took the fragments moving too quickly through radar range to make systematic detection impractical, leaving most of the swarm permanently uncharted. Occultation observations provide another detection approach. As fragments pass in front of distant stars, they briefly block starlight, creating a momentary dimming detectable by photometric monitoring. Networks of telescopes observing simultaneously from different locations can record occultation events and reconstruct fragment size and shape from the light curves. But the probability of any given fragment occulting a bright star remains extremely low. The fragment subtends a tiny angle on the sky. Stars are point sources, and the geometry must align precisely. Systematic occultation surveys detect perhaps a few events per year from known asteroids. Detecting 3I Atlas fragments would require extraordinary luck or targeted predictions of when and where occultations might occur. Dust production from small fragments continues even when the fragments themselves remain invisible. Each sublimating fragment releases dust that scatters sunlight, creating a diffuse cloud potentially detectable as extended emission in the comet's vicinity. Deep imaging that subtracts point sources and enhances low surface brightness features might reveal this extended dust component, appearing as a faint halo or streamers surrounding the bright tracked fragments. The total mass in dust could exceed the mass in detected fragments if most of the parent nucleus fragmented into pieces too small to track. The visible fragments might represent only the tip of the mass distribution. with the bulk distributed among countless undetected smaller pieces. The mystery of the swarm's total mass, the sum of all fragments large and small, relates directly to the parent nucleus size before fragmentation. Photometric observations before breakup provide brightness measurements, but converting brightness to size requires assuming albedo and activity level, both uncertain. Estimates suggest a nucleus perhaps 1 to 3 kilometers in diameter, implying total mass of roughly 1012 to 1013 kilograms, 1 to 10 billion tons. How this mass divides among tracked fragments versus invisible smaller pieces remains uncertain. If fragmentation was efficient, breaking the nucleus into many small pieces, most mass might reside in undetected fragments. If fragmentation left a few large remnants and scattered debris, most mass remains in tracked objects. Only took the inability to see most of the swarm to leave the mass budget ambiguous. The sum constrained only by the brightness of something that no longer exists as a unified body. The invisible fragments will never be catalogued individually. Their trajectories never precisely measured, their compositions never analysed. They form the anonymous majority, the uncounted population, evidence of their existence inferred statistically rather than observed directly. They continue outward bound from the sun, cooling and fading, eventually indistinguishable from the background of interstellar objects drifting through the galaxy. Another generation of wanderers between stars, their brief encounter with our solar system leaving almost no trace in the observational record. The opportunity to observe 3i Atlas closely spans only a limited window measured in weeks or months. Telescopes around the world coordinate observations during this interval, scheduling exposures during clear nights, balancing the comet's priority against other transient phenomena competing for limited telescope time. Each observation requires careful planning, predicting the comet's position in the sky using updated orbital elements, calculating optimal exposure times to maximize signal while avoiding saturation, selecting filters and instruments appropriate for the desired measurements. The comet does not wait for convenient scheduling or optimal conditions, moving continuously through space regardless of weather, equipment failures, or competing demands. The brightness of the comet and its fragments changes with distance from both Sun and Earth. Following the inverse square law, reflected sunlight intensity decreases with the square of solar distance, and again with the square of Earth distance. A comet at 2 astronomical units from both Sun and Earth appears 16 times fainter than it would at 1 astronomical unit from each. As 3 Atlas recedes after perihelion, it dims predictably according to these geometric factors, but activity changes introduce additional variations. Sublimation rate depends on solar flux, which decreases with distance, so gas production declines as the comet moves outward. Eventually, sublimation ceases entirely when surface temperatures fall below the threshold for significant volatile loss, typically beyond 3 astronomical units for water ice. The fading sets a practical limit on observation duration. Professional telescopes can detect objects down to magnitude 26 or 27 with long exposures, but such faint observations require excellent conditions and dedicated time. As the comet dims from magnitude 20 to 22 to 24, the required exposure time increases exponentially, and the number of telescopes capable of detection decreases. Eventually, the comet fades beyond the practical detection limit, not because no telescope could theoretically detect it, but because the investment of telescope time yields diminishing scientific return. Observers make final measurements, extract final spectra, capture final images, and then release the telescopes for other targets. The comet continues outward, now invisible, its observational record complete. The data collected during the observation window becomes the permanent scientific legacy, images stored in archives, spectra reduced to wavelength and flux tables, photometric measurements listing brightness versus time, astrometric positions providing coordinates at specific epochs. These datasets preserve what was observed, but they also encode what was not observed, gaps from cloudy weather, missing wavelengths from instrumental limitations, temporal cadence insufficient to catch rapid changes. future researchers analysing the data must work with what exists. Unable to command additional observations, the observational record frozen at the moment observations ceased. Some phenomena might have occurred but went unobserved. Outbursts, sudden increases in activity from impacts or cliff collapses or subsurface gas releases require continuous monitoring for detection. If an outburst occurs during the hours between observations, it might be missed entirely or caught only as brightening or dimming in the next measurement compared to previous trends. The actual peak brightness, duration, and evolution remain unknown. Small fragments separating from larger ones might appear in one set of images but not in earlier images. But whether separation occurred hours or days before detection remains ambiguous. Only took the discrete nature of astronomical observations to miss events happening continuously in time. Sampling a process rather than recording it completely. Different telescopes contribute different capabilities. Large aperture telescopes gather more light, enabling detection of fainter objects and measurement of fainter spectral features. Telescopes with adaptive optics achieve sharper images, resolving structures within the coma or separating close fragments. Spectroscopic instruments provide composition information at the expense of reduced spatial resolution. Polarimeters measure dust properties. No single telescope optimizes all measurements. So comprehensive characterization requires coordinating observations across multiple facilities, each contributing its specialized capability. The final picture emerges from synthesizing diverse datasets, each with its own strengths and limitations. Space-based observations avoid atmospheric interference. The Hubble Space Telescope achieves angular resolution impossible from ground-based telescopes except with sophisticated adaptive optics, and observes ultraviolet wavelengths completely absorbed by Earth's atmosphere. Infrared space telescopes like Spitzer or James Webb detect thermal emission and molecular features invisible from the ground. But space telescope time is even more competitive than ground-based time, oversubscribed by factors of 5 or 10, with observation requests exceeding available time many-fold. Securing space telescope observations for a transient target like a fragmenting comet requires urgent proposals, rapid review processes, and flexibility to schedule during brief windows when the telescope's orientation allows viewing the target. Some observations succeed, others are declined or scheduled too late to capture desired phenomena. Amateur astronomers contribute significantly to comet observations. With dedicated CCD cameras and telescopes ranging from 20 to 60 centimeters aperture, experienced amateurs conduct photometric monitoring, detecting outbursts, tracking brightness variations, and providing temporal coverage between professional observations. Their data, submitted to central clearinghouses like the Comet Observation Database, fills gaps in professional coverage and provides alerts that trigger intensive professional follow-up. The community of comet observers, numbering hundreds worldwide, forms a distributed monitoring network operating every clear night, ensuring that some observations occur even when professional telescopes remain unavailable. Only took dedicated individuals choosing to spend their nights tracking faint comets to create observational coverage impossible through professional facilities alone. The final spectrum, the last photometric measurement, the closing image each marks an end to direct observation, the transition from actively monitored target to archived data. The comet continues its journey, but humanity's knowledge of that journey stops. The narrative interrupted at the moment observations ceased. What happens to the fragments beyond detection distance remains unknown, knowable only through theoretical modelling, extrapolation from observed behaviour, inference from similar objects. The fragments cool, activity ceases, crusts thicken, and they become dark inert bodies coasting through interplanetary space, then interstellar space, invisible except perhaps to civilizations with far more powerful instruments or fortuitous trajectories bringing fragments close to their own stellar systems billions of years hence. Every interstellar comet carries within its structure a record of processes that occurred around a different star. Information about planetary system formation in environments beyond our direct observation. The study of 3 Atlas and its fragments provides comparative data. A single additional data point in the parameter space of cometary properties, solar system comets, studied extensively over centuries, define our understanding of what comets are and how they behave. But this understanding remains necessarily limited by sample bias. We observe only comets that formed in our own solar system, under conditions specific to our Sun's protoplanetary disk and subsequent dynamical evolution. The formation of planetary systems follows similar processes around different stars, governed by the same physics but expressed through varying parameters. A protoplanetary disk forms from collapsing molecular cloud material, inheriting angular momentum that prevents direct infall onto the growing star. The disk rotates, conserving angular momentum, while viscous processes transport angular momentum outward and mass inward, feeding the central star while allowing disk material to gradually spiral inward. Temperature in the disk decreases with distance from the star, creating snow lines where different volatile compounds condense water ice beyond roughly 3 astronomical units for a Sun-like star. Carbon dioxide farther out, carbon monoxide farther still. Comets form beyond the snow lines, accreting from ice-coated dust grains that stick together through gentle collisions. The disk's lifetime, typically a few million years, constrains the available time for comet formation. Observations of young stellar systems show that protoplanetary disks dissipate within roughly 1 to 10 million years, dispersed by photoevaporation from stellar radiation, blown away by stellar winds, or depleted through accretion onto the star or into planets. Comet nuclei must form before the disk dissipates, accumulating from smaller particles through collisional accretion. The timescale for growing kilometre-sized bodies from dust grains remains uncertain, depending on particle collision velocities, sticking efficiency, turbulence in the disk, and local density. Theoretical models suggest timescales of thousands to millions of years, but observational constraints remain sparse. Planet formation in the inner disk gravitationally perturbs comet orbits in the outer disk. Giant planets like Jupiter, forming within a few million years, scatter nearby planetesimals through gravitational interactions. Some planetesimals are thrown inward, potentially colliding with terrestrial planets and delivering volatiles to their surfaces. Others are ejected outward into distant orbits, forming reservoirs like the Oort cloud that surround the planetary system at distances of thousands to hundreds of thousands of astronomical units. Still others achieve escape velocity and depart the system entirely, becoming interstellar comets. The efficiency of ejection depends on planetary masses and orbital configuration systems, with multiple giant planets on eccentric orbits eject comets more efficiently than systems with single planets on circular orbits. The delivery of water and organic compounds to terrestrial planets represents one consequence of cometary bombardment. Earth's oceans contain roughly 1.4 billion cubic kilometers of water, equivalent to about 1.4 Dorstenwas 21 kilograms. If this water arrived primarily through cometary impacts during the late heavy bombardment period, approximately 4 billion years ago, and if typical comets contain perhaps 10 to 12 kilograms of ice, then roughly 1 billion comets would need to impact Earth. Estimates of the late heavy bombardment intensity suggest impact rates sufficient for such delivery, though asteroids from the outer main belt might have contributed comparable or greater water mass. The isotopic composition of Earth's water, intermediate between typical cometary values and asteroidal values, suggests mixing of both sources. Other planetary systems likely experience similar bombardment histories, implying that terrestrial planets elsewhere may have received water and organics through analogous processes. If cometary composition remains relatively uniform across different stellar systems, as similarities between 3I Atlas and Solar System comets tentatively suggest, then every rocky planet in the habitable zone of any star potentially received the chemical ingredients necessary for life. The emergence of life would then depend not on the availability of raw materials, which cometary delivery provides universally, but on other factors like planetary conditions, energy sources, and chance. Only took billions of comets impacting billions of planets around billions of stars to seed the galaxy with prebiotic chemistry, whether or not that chemistry ultimately produced biology. The diversity of planetary systems discovered around other stars shows that our solar system represents just one possible outcome of the formation process. Hot Jupiters, giant planets orbiting extremely close to their stars, likely migrated inward from formation locations farther out, disrupting any cometary populations and potentially scattering them into interstellar space at high rates. Systems with multiple Neptune-mass planets in compact orbits differ dramatically from our solar system's architecture. Systems orbiting red dwarf stars form in disks with different temperatures and chemical compositions than Sun-like stars. Each system's unique configuration produces different outcomes for comet formation, ejection rates, and properties, contributing to the population of interstellar comets wandering the galaxy. The age of 3I Atlas's parent system remains unknown but could range from millions to billions of years. Young system, still surrounded by remnant disk material and undergoing active dynamical evolution, eject comets at higher rates than old, settled systems. Old systems have already ejected most unstable objects, leaving only tightly bound populations in stable reservoirs. The observed flux of interstellar objects entering our solar system reflects the integrated contribution of all stellar systems in the galaxy, with young nearby systems contributing disproportionately due to higher ejection rates and shorter travel times. If 3I Atlas originated from a young, nearby stellar system, it might represent typical conditions in actively forming planetary systems. If from an old, distant system, it survived billions of years in interstellar space, its chemistry potentially altered by radiation processing. The question of whether life arose elsewhere in the galaxy connects to cometary chemistry through the delivery of prebiotic molecules. If amino acids, nucleobases, lipids, and other biological building blocks form commonly in comets throughout the galaxy, and if cometary bombardment delivers these molecules to terrestrial planets universally, then the chemical preconditions for life exist widely. Whether life actually emerges depends on additional factors beyond chemistry energy sources to drive reactions: liquid water as a solvent, sufficient time for complex organization to develop, stability against sterilizing impacts or radiation. But the first step, the availability of complex organic molecules, appears increasingly likely to be common rather than exceptional, each interstellar comet carrying evidence of the galaxy's organic chemistry. The mystery of life's uniqueness or ubiquity remains unresolved, but studying interstellar comets provides constraints on one piece of the puzzle. If all comets everywhere share similar chemistry, then the chemical starting point for life is universal, and differences in biological outcomes must reflect differences in planetary environments rather than differences in available chemical feedstock. If comets from different stellar systems show significant chemical diversity, then some planets might receive more favourable initial conditions than others, potentially influencing where and when life emerges. Only took measuring the composition of wanderers from other stars to begin addressing questions about life's distribution across the cosmos. Each comet a messenger carrying chemical information across interstellar distances. The fragments of 3I Atlas continue their departure from the inner solar system, accelerating relative to the Sun as they fall along their hyperbolic trajectories, then gradually slowing in the Sun's reference frame as they climb outward against the gravitational gradient. Beyond the orbit of Mars, beyond the asteroid belt, the fragments cool as solar flux diminishes with the square of distance. Surface temperatures that reach 200 Kelvin near perihelion decline toward 150 Kelvin at Jupiter's distance, toward 100 Kelvin near Saturn. Sublimation of water ice ceases entirely, the last wisps of coma dispersing into the solar wind, leaving the fragments inert and dark. Their brief period of activity concluded. Tracking stations continue monitoring the brightest fragments even as they fade, refining orbital elements with each new position measurement. The uncertainties in orbital parameters decrease with longer observational arcs. the trajectory becoming better defined as time baseline extends, but eventually the fragments dim beyond detection limits and position measurements cease. The last observation occurs perhaps 6 months or a year after discovery. The fragment faint but still trackable in the largest telescopes. Then cloud cover prevents follow-up, or telescope scheduling conflicts intervene, or the fragment simply becomes too faint even with long exposures. The observational arc ends, leaving the trajectory known with finite precision, future position predictable but with uncertainties that grow steadily as the fragment travels beyond the region constrained by observations. The orbital predictions extend forward through numerical integration, calculating where each fragment will be in 1 year, 10 years, 100 years. The predictions show continued outward motion, passing the orbit of Uranus in a few years, Neptune in perhaps a decade. Beyond Neptune, in the region of the Kuiper Belt, the fragments coast through the realm of trans-Neptunian objects, those icy bodies orbiting the Sun at distances of 30 to 50 astronomical units. But unlike Kuiper Belt objects bound to the Sun in elliptical orbits, the fragments pass through only once, their hyperbolic paths carrying them toward the heliopause, the boundary where solar wind pressure balances interstellar medium pressure. The heliopause lies roughly 100 to 120 astronomical units from the Sun, depending on direction relative to the Sun's motion through the local interstellar medium. Voyager 1 crossed this boundary in 2012 after 35 years of travel. Voyager 2 followed in 2018. The fragments of 3I Atlas, travelling faster than the Voyager spacecraft, will reach the heliopause in perhaps 30 to 50 years after perihelion passage, crossing from the region where solar influence dominates to the region where interstellar conditions prevail. No instrument will observe this crossing. The fragments are too faint, too far away. Their passage marked only by calculations showing predicted position, moving beyond the modelled boundary location. In the interstellar medium beyond the heliopause, the fragments encounter conditions different from those within the solar system. Particle density increases slightly, from roughly 5 particles per cubic centimetre in the outer solar system to perhaps 30 particles per cubic centimetre in the local interstellar medium. These densities remain far lower than any laboratory vacuum, but over years and centuries, accumulated impacts with interstellar hydrogen atoms erode exposed surfaces at nanometers per year. Cosmic rays, unshielded by the heliosphere's magnetic field, strike more frequently, continuing the radiolysis that alters surface chemistry. The fragments gradually accumulate in irradiation crust, chemistry transformed from pristine comet material into something resembling the surfaces of long-exposed interstellar grains. The temperature in interstellar space equilibrates at approximately 3 Kelvin, the cosmic microwave background temperature slightly elevated by absorption of starlight from nearby stars. At such temperatures, all volatiles remain frozen, even molecular hydrogen and helium, though in practice comet nuclei contain negligible amounts of these lightest elements. The fragments become inert ice rock mixtures, thermally stable, changing only through the slow accumulation of radiation damage and the even slower erosion from interstellar particle impacts. Timescales for significant change extend to millions or billions of years, the fragments effectively frozen in time, preserved in the cold and dark. Their trajectories through the galaxy follow the gravitational potential created by stellar mass, dark matter. The fragments orbit the galactic center along with the Sun and nearby stars, all moving at roughly 220 kilometers per second in the galactic rotation. But the fragments' velocities relative to this rotating frame, their peculiar velocities, differ from the Sun's by tens of kilometers per second. The separation velocity imparted during ejection from their parent system plus or minus the relative velocity between the Sun and that parent system. Over millions of years, these velocity differences carry the fragments away from the Sun's neighbourhood, traversing tens or hundreds of parsecs, encountering different regions of the galactic disk. Encounters with other stars occur rarely, but inevitably over long timescales. The stellar density in the Sun's neighbourhood averages roughly 0.1 stars per cubic parsec, so a sphere 10 parsecs in radius contains roughly 400 stars. A fragment travelling at 30 kilometers per second traverses 10 parsecs in roughly 300,000 years, passing through volumes occupied by hundreds of stars, though most passages occur at distances of light years rather than the close approaches measured in thousands of astronomical units that would gravitationally perturb the fragment significantly. Perhaps every few million years, a fragment passes within a light year of a star, close enough that the star's gravity slightly alters the fragment's velocity. Closer encounters, within 10,000 astronomical units, might occur every billion years. Rare events that significantly redirect trajectories. The probability that any 3I Atlas fragment will someday enter another stellar system's planetary region remains low but non-zero. Most interstellar trajectories pass through the vast empty spaces between stars rather than through the compact planetary system surrounding them. But with billions of stars in the galaxy and billions of years available, rare events eventually occur. Perhaps in a billion years, one fragment approaches another star to distances comparable to our solar system's scale, passing through that system's Oort cloud, or even entering the inner planetary region. Inhabitants of that system, if any exist, might detect the visitor, measure its trajectory, determine its interstellar origin, and wonder about its history and source, just as humanity wonders about 3 Atlas's origin, the cycle repeating across stellar systems and geological timescales. The fragments themselves carry no record of their passage through our solar system beyond the physical changes induced by solar heating, the brief warmth near perihelion, the sublimation that stripped away surface layers, the thermal fracturing that perhaps initiated further fragmentation. These events altered the fragment's structure and composition, but left no written record, no marker identifying where and when they occurred. A future civilization analysing a fragment would find a comet nucleus with specific properties, perhaps inferring that it experienced solar heating at some point in its history, but unable to determine which star it approached or when, only took the silence of material evidence to make history unrecoverable. Each comet carrying physical scars but no narrative of their origin. The long silence stretches forward through time, the fragments receding into darkness, cooling toward the background temperature of space, invisible and untracked, their trajectories calculated but unverified, their fates unknown. They drift through the galaxy as they drifted before entering our solar system, patient travellers through the cosmos, existing in the margins between stellar systems, neither born into any system's gravitational embrace nor destroyed by any catastrophic encounter, simply persisting through the endless cold, waiting for nothing, moving according to gravity's gentle imperatives through a galaxy that takes no notice of their passage. The darkness between stars holds more silence than can be measured. The fragments drift outward, growing colder with each passing year, their surfaces recording nothing, their interiors preserving ice that formed before memory. No telescope follows them now. The calculations end at prediction, the story at inference. What happens beyond observation lives only in equations, in models of gravitational fields and cosmic timescales, numbers describing motion through volumes too vast and too empty for human comprehension. Perhaps the fragments tumble slowly as they travel, rotation imparted during separation gradually slowing through the subtle friction of outgassing that has long since ceased. Perhaps they maintain whatever spin they carried away from the sun, angular momentum conserved in the absence of torques, turning once every few hours through darkness that never changes. The distinction matters to no one, no eye watches, no instrument measures. The fragments exist in a state beyond observation, real but unknown, continuing but unwitnessed. In 1,000,000 years, they will have travelled 1 light year. In 10 million years, 10 light years. The galaxy rotates. Stars drift in their orbits around the galactic centre. The fragments move with them and through them. tracing paths that will never be reconstructed. They become part of the interstellar population, indistinguishable from countless other wanderers. Ice and rock adrift between suns, neither arriving nor departing, simply present in the cold. The sun continues its own orbit, carrying Earth and the other planets around the galaxy at 220 kilometers per second. The separation grows. What was once a visitor from distant space becomes distance itself, geometry expanding between observer and observed until the distinction loses meaning. The fragments were here, briefly, close enough to detect and measure and study. Now they are elsewhere, too far for any observation, known only through the data archived from those few months when sunlight made them visible, and still they travel, through regions where molecular clouds gather, thick with dust and forming stars, through voids where stellar density drops and darkness deepens, through spiral arms, and between them, the fragments carry within their ice the chemistry of another star's environs, preserved through the aeons, slowly altered by radiation but fundamentally unchanged. Ancient witnesses to processes that occurred before our sun ignited, perhaps, or during the long Middle Age of galactic history when stars formed and died and formed again from enriched material. They continue, they will always continue, until impact or dissolution, until capture by some star's gravity or fragmentation through collision with interstellar debris. They persist, ice and dust, loosely bound, tumbling through the void. The three-eye Atlas swarm, scattered now beyond recognition, each fragment alone, unreachable, silent. The galaxy contains them as it contains everything, indifferent to their presence, providing only the gravitational structure through which they fall, forever falling through a cosmos without floor or ceiling, without beginning or end to their trajectory. Only middle, only the endless now of motion through space. The story ends where observation ended. The rest is extrapolation, imagination, mathematics. The fragments themselves remain, unconcerned with narrative, participating in no story, simply being what they are, pieces of ice and stone, moving through the dark, cold and patient, requiring nothing, offering nothing, present in their own silent way, travelling through the cosmos that takes no notice and provides no comfort, only distance, only time, only the slow unwinding of trajectories calculated but never confirmed, predicted but never witnessed. Continuing in the long night between stars, sleep finds them there and leaves them there. The universe, vast and cold, holds them as it holds everything, and the darkness, complete now, offers no more answers,